Okay, this first video I'm going to show you how to calibrate a detector using HexRD's old graphical interface from a powder pattern. If you don't have a powder pattern, then we can skip ahead to the next step, but if you do, then this is the procedure. So on a Mac or Linux or even Windows type system, what you do is you open a terminal. It's going to give you a command line, and if HexRD is properly installed, if I just type the command HexRD, it's going to come up with all of the options, command line options for the thing here. I just installed it, so it's probably parsing things right now, but or maybe I didn't. Oh, there we go. All right. So it tells you all the options that you can type in here. The one we want is the graphical user interface, so it's HexRD space GUI on the command line, and this will fire up the old graphical user interface written in WX Python. Great. So there's a few materials that are loaded standard: Syria, Diamond, Lab 6, Ruby, and Silicon, common calibrant materials. If we are, in this case, I have a Syria pattern that we're going to use. So for something high symmetry, max sum of squares for the HKLs of 100 gives us plenty for typical setups. The only thing you might have to change for your particular instrument down here is the energy that you're using. At Argon, we often use the gold K alpha edge, and that is 80.725 keV, so we don't need to change anything here. So I go into the reader tab here. There's a couple things. If there was you can store a list of these things that are interfaces to read different scans, where you basically aggregate raw files together into something that means a scan. For a calibration pattern, well, first of all, I can give it a unique name here. So we'll say CEO2 calibration. Image mode for the calibration images I have is a bunch of single frame images. Frame aggregation, since they're single frame images, I only want to look at one at a time, so we're going to say just single frames here. Image orientation, now this is important for your particular setup. You have to figure this out. The flip mode, in terms of when you read the raw file and how it would actually be sitting in the frame, the way the software is anticipating the array, meaning the image, is at the upper left corner, or entry 00, if you're looking at it as an array, would be the upper left corner of the detector as you looked at it from the photons perspective, so looking at the front of the detector. So it so happens for the GE detector we were using at Argon at the time, it was a vertical flip mode. There were dark images. You can do none, but I have a dark image file that I can go and select here. So it was under shared. Let's see, my dark image. Well, I have more. It was this one here. And now I select the image files. The beauty when you're calibrating from a powder pattern is if I select more than one, in this case a typical procedure is to take a calibration pattern with the stage at 0 degrees and 180. Since you can't put the powder exactly where the rotation axis is, if you take two or more images or pairs of images at 0 to 180 degrees, you can average the results. The software will do this automatically for you and give you the average distance. So I have those two files here. So when I do load, it's going to load the first one. And lo and behold, here's a Syria powder pattern that we're looking at here. It's a nice sanity check with the Syria pattern. I know the wires from the beam stop point, up and to the left, so I know my flip mode is right here. I have two frames that I'm going to fit, so you can see they're roughly indistinguishable here. So why don't we go ahead and start to build our initial guess. So if I click on show rings with the parameters I have here, that's where they would appear on the detector. So it's a pretty straightforward thing. If I zoom in on these inner rings here, they're most sensitive to position. you can actually move things live here. Let's make this a little bigger. So it looks like I need to, for sure, I need to move things up. Don't ask me why in the Mac the left arrow is up and the right arrow is down. It looks a little different on different platforms. So it's about centered. I got to move it to the right. Let's change the color map here. Okay, that looks good. Now it's zoomed out, so that means that the distance has to be bigger. Recall it's somewhere around 1050. Oh yeah, there we go. So it's looking pretty good for a start. Let me zoom out over here so I can just see all the rings I've selected. Remember, those are the first 5 that are selected here. Now if I open this editor, I can select one ring, and you'll see it would be just that one. Typically doing the first 5 in this case is good. We can do the first 6 if we want. You can shift click and control click here. If you open that, you don't want to change things, just hit cancel, because if I hit OK, notice no rings are selected because I didn't select any. The ones that aren't selected are grayed out, so you have to either hit cancel to not change things or select things and hit OK. Other important thing is for the fits is this range selector here. Now 0.002 radians is a little tight. That's 0.01 degrees plus or minus. Place I usually start with a rough guess like this would be maybe 3.5, which would be 0.2 degrees. It's okay if things overlap. You just want to make sure that these dashed ranges that your ring that you're trying to fit in each image doesn't go outside the dashed ranges there, because it will give it an error if it does. And sure enough, for both, it looks pretty good. So zoom back out here, go back to the detector page. The things I want to fit with such a few number of rings are these first 5 parameters. You cannot fit the detector's tilt about its own normal with powder pattern because it's axisymmetric. Nor can you fit the chi tilt with anything here. It's just meant to read it in this case. These last 6 parameters are distortion parameters, but we don't have much information to fit them with only those 5 rings, so we're going to take those off. I will note that if you change these things, you do have to hit enter in these boxes for it to actually accept your changes in the text boxes here. Okay, so we've got what we want to fit. I'd select binned fit here, since the default settings are fine for this, for doing a quick initial estimate. Let me bring the terminal here because it's going to echo back to terminal when I actually hit this. You can see what's going on. So when I run fit, you see a bunch of things. It's actually doing the fit and the least squares problem, and the residuals going down to something that we'd expect. Fit the first image, fit the second image, and now it's going to average the results, and we'll update things in the field here. So at this point, we have a decently calibrated detector. We can now, with the binned fit, I can include rings all the way out to the edge of the detector, which would be the last complete ring on the detector. Looks like it's probably, for safety's sake, will be this one here, 260. Doesn't fall off the detector. Up here. Now we could do this guy. Don't worry about duplicates because it already crushes them out when it does the fit. So it looks like up to here is probably where we have. We don't want to use that guy because it's off the edge of the detector. So we'll go up to 353. Looks pretty good. Now that we fit a little bit better, I can probably do a little bit tighter tolerance, so it will run a little faster. Just to double check that when I look over my images that since the images that are at different distances, it's good to double check that things don't fall off the detector. This one is pretty near the center, so it hardly moves between frames. So that's fine. Now with that entire data set here, let's go and now refine these first 3 coefficients for the detector distortion. And I can also let's do some more azimuthal bins. Now in these spin controllers, I have to hit tab for it to accept it. What this radial rings per bin is how many bins it's going to do radially across this pixel range. It's going to try to fit with the native pixel sizes in the detector. So one way to look at how it was oversampling is up here. When it started, number of pixel divisions here that it's using is 1. I can oversample a little bit and turn this into, say, 30. So it would fit. See, number of pixel divisions was 2 when it's doing this. So now it's doing all of these rings with finer azimuthal steps. So the number of azimuthal bins is now 60. So 6-degree wide bins. It's taking a little longer to fit because it's fitting all those things in the detector, but not much longer. And here we go here. Now, what would have happened if I picked a range that went off the edge of the detector? It would have fed nans into the least squares, and it would have stopped at this point and just said in here, error from least squares. Now, nothing is wrong. You can go and restart the fit by selecting rings that are only on the detector for the bin fit. So there we go, it's done, and I have now a pretty good detector calibration at this point. So what I want to do, well, first, before I save any files from this interface, this is a little goofy thing, I want to save the experiment. So let's call this Ruby new.exp. You have to include the .exp when saving the whole experiment. This will save the state of the graphical interface where it is right now. Oh, okay, so it's already giving me an error. So the fallback is to, I can save each one of the inputs into each one of these panels independently. So go to the detector here. I can save the detector, and I can call this GECO2 dot, we'll call it .par. That's just a text file. So I've exported the detector. The materials file I can save as well. Remember the settings I used. We'll just call this materials.cpl. That's for a cpickle file. Sure, I'll paste it. And then the reader, I can save this as well. And it saves the list of readers, and I can say readers.cpl. That's also a cpickle file. And there you have it, a calibrated detector.